All right, we're gonna start our next unit, and it's on logarithms. So a logarithm, we're gonna start with today just looking at what it is and how the graphs compare to exponential graphs. So basically the idea is a log graph and an exponential graph are pretty much the same, they're just one's a reflection or the opposite of the other. So we're going to look at what each of them are, and you're going to see that because they're opposites of each other, the graph features are almost the same as well. So we're going to start with looking at an exponential graph, just a basic one. So if the equation was y equals 10 to the x, we know from the last unit that it's going to be an exponential curve, and it will, remember our standard form was a times b to the x, so in this case our a is 1, there is no number in front of the 10, and our b is 10, so because of that we know that it's going to cross at 1, we're going to have a y-intercept of 1, and the 10 means it's going to get increasing, so our graph would do something like that, right? We end up getting an exponential curve crossing at 1, and it's increasing because it's going up to 10. And when we do those ones, we know that the graph has one y-intercept. The y-intercept in this case is 1. Right? So that's our y-intercept. It's at 1. We have no x-intercepts. Okay, the graph just follows the x-axis. I kind of crossed it a little bit there, but you can get the idea. And we know that the domain was any real number for x, and our range was greater than 0, so y is greater than 0. And then we know that it went from quadrant 2 to quadrant 1, and that was it. So now when we do, I'm going to change colors here, and now we're going to do the log graph. So the similar graph of 10 to the x is just log to the x. Okay, the 10 I'll explain tomorrow where the 10 goes to make these same, but trust me for now that these are pretty much the identical graphs, just opposite of each other. So you could actually plug that in on your calculator, go to y equals, put in log x, and when you hit graph, what it's going to do is it's going to be basically the mirror reflection of the graph. So it'll start low, and it's going to go something like that. So this time, it's going to, so you can see what I mean when I say diagonal reflection. It's sort of like if we drew a diagonal line like that down the middle, you can see one graph is just sort of a reflection of the other. So for the log graph, you can see that now there is no y-intercepts. So our y-intercepts, there's none. And our x-intercepts, we have one of them, and in this case it's at 1. So you can see it's just the reverse of the exponential one, and our domain and range also get reversed. So our domain will be x is greater than 0 this time, and our range will be y is any real number. And it'll always work like that for any graph, doesn't matter what the numbers are, you'll always get the similar type of features for the graph. Okay, so now what we're going to do now is we're going to look at how do these graphs compare. So the first one we're going to look at, let's do y equals 3 log x. So on your calculator, type those in. Just type in y equals, go to the y equals button, put in 3 log, and I think your calculator gives a bracket, so just put log x inside the brackets. Hit graph, and what you're going to see is you should get a graph that does something like that. So it's still going to cross at the point 1. You're still going to have an x-intercept of 1, and our graph will just continue on and on for both directions. So now let's see, what would it look like if we graph y equals 14 log x. So plug that in on your calculator, graph it. You're going to see that because it's 14, it's going to be bigger. The graph is going to be more like a straight line. So you end up getting sort of a taller type graph. You can change your window settings and zoom in and so on, but you should get a pattern something like that. And then let's also try a small number like a half. If you put in a half log x or 0.5, it doesn't matter which way you enter it. You're going to see this one ends up being sort of similar again, but it's going to be lower. Okay, so you can see that front number just sort of changes the steepness or the height of the graph, but they all go through the point 1. That's never going to change. So our x-intercept is always still 1, and the rest of the graphs, they always go down, follow the y-axis on the bottom, and the top just sort of changes depending on the size of that number. Okay, now the only other thing we're going to do is we're going to look at what happens when you have a negative in front. So if I put in negative 4 log x, the graph is similar, but it sort of does the reverse. We end up getting a downwards graph. Because it's negative, it's going to decrease. So when you type this one on your calculator, it's still going to go through the point 1, but the graph ends up going downwards instead of upwards. So it's going to be just sort of a reflection of the one that we did just recently. So our positive graph goes upwards, so that would be what negative 4 would look like. Let's just draw a positive 4 just so you can kind of see the difference. So it'll be starting on the bottom, it'll go through 1 and go up. So you can see they're pretty much identical graphs, just the positive one is going upwards, the negative one is going downwards. It's going to be decreasing. And that's pretty much it for logarithms for today. So we just wanted to look at how to graph them. So type them in on your calculator, plug in the equation, see what the graph looks like. For all the ones that we're looking at today, the x-intercepts will be 1, and they're either going to be increasing or decreasing just depending on what that number is in front of the graph. So our standard, let me just give you a few quick notes here. So our standard equation that we're looking at for logs today is y equals a log x. So that a number just changes how tall it is, and whether it's positive or negative, that's about all that changes. Where these log graphs, we're going to do a little bit more tomorrow figuring out different ones, but where these log graphs are in real life, when we did the last unit, exponential graphs quite often turned out to be applicable for interest and banking and things like that, where log graphs work out too. So the applications end up being things like pH. So if in science the pH function is actually a log graph, it follows the same sort of pattern. Another one we do is the Richter scale, which measures earthquakes. Okay, so the scale that they use to say how strong an earthquake is, whether it's a 5.8 or 4.2, it basically follows a log graph. And another one we do is decibel level, which is sort of the loudness. So you go to a rock concert or whatever, and they tell you how many decibels it is. So a decibel of 100 it follows a log graph. If it was 100 or 92 or decibel of 60 or 120 or whatever, it would sort of follow that same sort of pattern. So it doesn't just make a linear increasing. All of these kind of things, if you were to graph them, you'd end up getting a log type graph. So it makes this sort of curvy graph type shape. And they're a little bit different for each one, but they all sort of follow the same pattern. So that's it for today. So this first part of the lesson today, we're just looking at what a log graph is, draw the graphs, figure out some features, match graphs to equations, and so on. So that's it. So on the worksheet, the 7.1 worksheet, you should be able to answer all those questions. So that's it. We'll do some more tomorrow. See ya.